begin my presentation, I did my work on IFC-based schedule optimization, and this was supervised by Professor Cheroushek and co-supervised by Dr. Parenche. So the main problem that I was trying to solve is that the construction schedules are incredibly complex. The things that go into thinking about any construction schedule, apart from the predecessor and successor relationship, usually are time constraints and cost constraints, which must be kept to a minimum. And in addition to this, we have labor costs, we have labor productivities, and all these are usually put together depending on the skill of the scheduler and their experience. So the same resources handed to two different schedulers will result in two different schedules. So these problems attempts have been made to solve them in the past with methods like linear programming. However, they are considered non-deterministic polynomial time problems. That means they cannot be solved in a short period of time or in a known period of time. So they are incredibly complex. So methods to address this exist. So meta-heuristics and specifically evolutionary algorithms have been studied before. And BIM as an informational container for 4D solution has also been studied before. However, these studies have not been done, not many of them have been done in concert with each other together. And so this study proposed a joint solution where IFC is used as an informational container, specifically with the global unique identifier, together with evolutionary algorithms to solve multiple objective and multi-constrained construction and demolition schedule problems. This was done by reviewing literature, by developing a mathematical model, and finally by generating optimal solutions for two case studies. An overview was done of the literature, first of all, in which I surveyed in the past, in the 20th century, scheduling methods that have existed. In the first half of the 20th century, we have more manual methods, which, even though they were manual, formed the foundation for how we interpret and how we work on schedules, even using more automated methods today. So from the critical path method to PERT, linear programming, and Gantt charts, these were what were predominantly in the first half of the previous century. In the second half, where computers started coming into being, or coming into being invented and such, and algorithms were used to try and solve problems more and more. So we began with simple methods like branch and bound and constraint programming and local search algorithms. And then we also had automated job shop scheduling, where we were trying to use the algorithms that we had created in an automatized way in order to solve that. However, again, these complex problems were so incredibly complex that eventually what came up in the late 1980s and afterwards were evolutionary algorithms in a bid to solve these challenges. Now, how an evolutionary algorithm works and what makes it special or better than the other ones is it works with a large search area, larger than the other methods used. And it initializes a set of populations. In our case, each population will denote an entire schedule from start to finish. Okay, each of the individuals in these populations are then evaluated using a fitness function or objective function to see whether they are up to par. For us, this would mean that they follow the successor-predecessor relationships, and they make logical sense in terms of a building. For example, you cannot start building from the 4th floor, you have to start from the foundation, and you can't start demolishing from the foundation either. So that is where the evaluation comes in. Two individuals are selected and crossed over and mutated, and their genes passed on to two new members of the next generation, which will have good genes, quote unquote. And this, once the number of children have reached the same number as the initial population, this process is done again and again and again until the number of generations specified. The final solution is usually presented in the form of a Pareto optimal set that you can see there. And this Pareto optimal set shows the optimized solutions. So from research, we found that IFC had been studied for 4D use, and evolutionary algorithms like the NSGA2, which is what we used in the study, had been proven to be highly effective for complex multi-objective and multi-constraint problems within construction. However, when studied together, like using BIM, and IFC, or using BIM, and optimization methods together. The first problem was either they were only used, BIM was only used for 3D data, in the sense that it was to visualize 3D data, and then other methods like work breakdown structures would be used to link that with the, to create activity IDs, and then parts of it would be optimized. Or it would only be used post optimization in order to visualize the schedules, or it would incorporate heavy manual and scheduler dependent workflows. For example, there was a study where the scheduler would come up with the schedule manually, and then only certain overlapping items would be optimized. So again, we are trying to solve this by using the IFC as a container, and specifically to use the global unique identifiers for each element to feed in directly into the optimization module. How we did this is by the use of a mathematical equation, which is the objective function. So we are trying to minimize cost and time while paying attention to the task order, that is TI. How we did this was by envisioning the chromosome that the NSGA2 will create in terms of a data frame. So here we have a data frame which is like a matrix-like structure, and we have teams, which are the columns are the teams, and the rows are the elements. Okay, so each element denotes a row. Each row also denotes a phase, which I will explain later. But by arranging it this way, we are able also to calculate cost and time. So we have the productivity of each team and the cost of each team. The time is volume of productivity, and therefore the total time is the sum of completion times in all columns, and the total cost is the time the time of each column multiplied by the specific cost of each column, which denotes the cost of the team, and then added all that together to get the total cost. All right, so the aforementioned equations are going to be, or were done within R, which is the programming language used for this task, with two inputs, that is the precedence matrix and the labor data. You have heard of the precedence matrix before from my colleague Andre Mantelato, who is also the person who created the methodology that was used in this study for the creation of the precedence matrix specifically. So this contains what is important to us. The data that is contained here is the element GUIDs, their volumes, and the IFC class and the predecessors. Okay, and then the labor data is the team costs and productivities. So the element volumes and the team productivities and costs all play together within the calculations as mentioned earlier. Four objects were used within R. The chromosome data frame, as I have explained, and a similar data frame to the chromosome one, where the element completion times were stored, and then two vectors, a remaining list and a completed list. We start with the full remaining list, and as each element is built, it is added to the completed list and removed from the remaining list in the order of construction, that is the schedule. So a repair strategy was created because what an evolutionary algorithm is essentially a blank slate. It is a general tool that can be used for optimization. However, you have to include domain-specific information by yourself. So in order to do that, we created a repair strategy so that we can fix the chromosomes, because NSGA2 will initially give us a random number, like a random assortment of genes inside the chromosome, and these genes do not necessarily adhere to the predecessor-successor relationships as given to us in the precedence matrix. So we select the first gene. If it doesn't have any predecessors, or it has completed predecessors, we assign it to a team, and then we calculate the time and we remove it from the remaining list. If it doesn't pass this test, that means it cannot be built. We cycled to the next remaining element. Then when the phase is full, we calculate the shortest element time, and then every other element goes to spill over to the next phase. We keep doing this over and iterate, and when only one element is remaining, it is assigned to the final team, and everything else is turned into zero. So we had two case studies that we used this methodology on. The first one was a demolition project, and the second one was like a simplified example of a construction project. The demolition project had 711 elements, and we it was conceptualized that manual deconstruction methods were going to be used because of circularity of demolition of demolished materials in order, for sustainability. So the precedence matrix was extracted from the BIM model and input into R, labor costs and productivity sourced from industry data, and then NSGA2R was the package used within R to do this optimization. 4 different runs were executed and schedules generated, as you will see. Okay, so the first run that we did had 5 teams with 12 chromosomes and 12 generations. The teams, the output we got from this was from the 12 chromosomes that have, like the initial population had, we only had 4 of them being optimal, Pareto optimal. The lowest time here was, as you can see, 3,370 hours, and the lowest cost was 3.35 million. A second run was done where the population was increased and the number of generations increased in order to get better solutions. So here you see a Pareto optimal set increasing to 11, right, from the initial 4, because the initial population has also increased, but the time and the costs are getting lower. In order to improve this even further, we ran a third run, this time making the teams double, that is 10, but with the initial population of 12 and 12, so that it can be comparable with the first run on time. And as you can see, the time is even getting lower. Like, we are getting more optimized time results. Here we had a Pareto optimal set of 8, showing that resources, when they're increased, will also increase the value of the they will increase the value of the results. So with this first 3 runs in mind, a 4th run was done, 10 teams, 48 population of 48 and 50 generations. This resulted in 15 Pareto optimal solutions and the lowest time and lowest cost yet. However, we are comparing the cost with just the previous one, because resources have been doubled, which means paying the extra 10 teams, the extra 5 teams would also have doubled. But the cost, the time, as you can see, is getting lower. And the Pareto optimal, the Pareto, the graphic that you can see there shows the Pareto curve. Okay, so what you can see, the numbers here in the middle are actually the schedule that is output. All right, so this is a schedule of 711 elements. I couldn't fit all of it in there, but as you can see, the first element corresponds to an IFC wall that you can see from the building, and the last one corresponds to element 506, corresponds to the slab, which is the final element. So you can see that this actually shows that this deconstruction is being done in the logical order. A second optimization was done. This one was for a 4-story structural building with 290 distinct elements with the same methodology for before. However, curing was not taken into consideration, which is like normal when we consider prefabricated elements. And we had 2 runs done. One with 6 teams, 24 chromosomes and 25 generations, and the second one with 12 teams, 24 chromosomes and 25 generations. You can see here the output that we had. The Pareto optimal number of schedules that were generated with the first one is were 7, and in the second one there were 12. We had a low time getting even lower. Again, we can't compare these two on cost because we have doubled the number of resources. There are 12 teams, so the cost wouldn't be the same, but you can see the time is going down. The table that you can see there at the bottom is a table showing the processing time that it took. So the caveat with this methodology is it actually takes processing resources, and since I was using an older processor, these are the times that it took. It's very interesting to note that the most complex problem, the demolition problem, with 711 elements and 48 population of 48, generation of 50, took 14 hours 16 minutes. However, if this was being done like out there in real life on a good computer in industry, what we would probably do is increase it to 100, a population of 100, the generation of 100, and this would give even better results. And finally, to conclude this work, we considered it successful, and as the system proved itself to be flexible, demonstrated by both case studies. And so for future work, we would probably want to modify the demolition assumptions so that we can account for machine-based deconstruction, because this comes with safety concerns, i.e. the people cannot be in the same place that the machines are deconstructing, and so that is something else that can be optimized. The inclusion of curing times also for in situ elements, and breaking down the elements into constituent parts. So we are not generally calculating for concreting, for example. We are also, we are considering the formwork, we are considering the reinforcement, like a more granular way to control the optimization. And further streamlining of the integration, obviously, of the GeoID data that is possible. And finally, the most important bit would be to actually put it into practice in a real-time project in order to see, to work out the kinks and refine it even more. Thank you.